Check it out now, y'all.
NanoHUB online instruction.
Well, this is the final lecture after a very long semester, and I thought I would just try to summarize some important themes that we've discussed throughout the semester related to this course. I think it's important for you to realize that we've primarily focused on topics that were developed roughly between 1880 and 1930. And all this work that we've discussed this semester has been done largely without computers, without the internet, without cell phones, without iPads. It's just people sitting down in rooms thinking about a problem and working out equations. The principles that were developed in this 50-year time span, the principles of quantum mechanics, really form the foundation for virtually all of today's advanced technology. So it's a truly remarkable accomplishment that spanned this 50-year period of time. The other thing that's always amazing to me is that if the math is good, the predictions, no matter how crazy they may sound, tend to match experiment. So, when you're working through some of these formulas, you can't help but wonder if any of this math has any relevance to experiment. But in fact, if the math is done properly, there's some very startling predictions that in fact do match experimental data. So I always find that kind of interesting. The primary goal of this course is to teach you how to think using the ideas of quantum mechanics. I must say we've just scratched the surface. A lot of the answers we've come up with are easy answers. Sometimes you have to distrust them. And to work in this business, you almost have to become a professional skeptic because a lot of the results that you achieve are not intuitively obvious. What have we learned? Well, we've primarily focused on the physics of the atom and the statistics that govern particles in a system with quantized energy levels. That's been the prime focus of all the lectures. Along the way, there have been brief excursions into condensed matter, special relativity, and nuclear physics, right? And we've tried to apply some of these concepts to these diverse fields just to give you a sense of how these different areas are interrelated. So I truly hope that you've learned a set of new concepts. And to be honest, I can only open the door. You must enter it by yourself. I'm sure you didn't understand everything we talked about, but the concepts that we discussed and how they're interconnected, right, I think will provide you with a very strong foundation as you move forward in your engineering careers. So best of luck in that endeavor. Where have we been? It's always a fair question to ask that. And so I tried to make some sort of a map that outlines in one slide the topics that we discussed. As you recall, back at the start of the semester, we reviewed some of the important principles of classical mechanics. We took a rapid diversion into Maxwell's equations and electricity and magnetism. We reviewed some of the fundamental properties of radiation that were known in the 1850s and 1860s. And then we used that background to crisscross this field of quantum physics more than once. We extended the discussion to include the statistics of quantum particles. So we've done a few weeks of lectures in statistical thermodynamics. We've applied the principles of quantum mechanics and statistical thermodynamics to discuss a few important problems in condensed matter. Once we finished with that discussion, we made a brief excursion through the realm of relativity. We also very quickly went through some basic concepts in nuclear physics. And then to end the course, we touched on some applications of nuclear physics to astrophysics, just to give you a sense of how these different topics are built one on top of the other. So when we started, it may not have been clear where we were going, but this is an attempt to map out our path through the various topics throughout the semester. There are many underlying themes in this course apart from the knowledge of quantum mechanics that we discussed, and I'd like to just go through those themes very quickly. We have learned that perhaps the greatest challenge of science is to ask questions that can be reduced to a manageable solution. What's always impressed me is that you can always formulate a problem in science or engineering that can't be solved, but it takes a real special knack to formulate a problem with a solution that means something. So by and large, the topics that we've discussed this semester were the efforts of men who were able to have enough insight to pose a problem that could be solved in a manageable way. The other thing that we learned was that there's this time lag between when an issue is first raised and when it's finally resolved. And that time lag often spans 25 to 50 years. So that seems to be a time constant that's independent of the topics that we've discussed. It just seems that good things take time, and to completely understand a subject requires a significant amount of work in years of time. The other thing that we've learned about was that the rules at the bottom of matter are completely different from the rules at the top. And if you didn't understand that concept when the class started, I sure hope you understand it now. We also hope you realize that your head will not explode if you learn something really new. And part of my purpose this semester was to dispel this quantum weirdness myth, which I often hear from engineers, where they just say, well, this is a quantum problem and the solutions are weird. Well, the solutions aren't weird. They're just, the rules are different at the bottom than they are at the top. And if you can't cope with that realization, then you end up promulgating this quantum weirdness myth. So I hope you take that away from the course as one of the themes. And lastly, we tried a new course format this semester. We've given you more opportunities to think about the topics before we actually discuss them in a discussion section, and I hope that enhanced your ability to understand what's going on with this very interesting topic of quantum mechanics. It's kind of useful to give you an impression of quantum mechanics and quantum theory from, let's say, a 50,000-foot view. And if I were really pushed very hard, what are the 2 or 3 fundamentally new ideas that have driven this field of quantum mechanics, I would have to come up with three concepts. This concept that light is a photon was a seminal advance, and that permeates an awful lot of modern thought. The idea that particles have a wave nature associated with their motion, that was a radical idea in the 1920s, but it's turned out to be crucial in understanding the properties of quantum systems. And then lastly, the idea that both light and particles, and I mean particles like electrons, possess this intrinsic angular momentum or spin that only have discrete values. That gives rise to a multitude of predictions and allows you to really understand let's say, the structure of the periodic table of all the chemical elements. So those 3 ideas, I think, form the basis of an awful lot of the quantum theory that goes on even today. I will say that anything worth doing is not easy. I understand that there were many challenges for you along the way throughout this semester. You particularly had to make time to view these online lectures in a consistent way. There were many lecture quizzes that were designed to help test your understanding of these lectures. The homework problems tended to be rather complicated, and of course you had to prepare for exams. So there were many opportunities to get frustrated and to fall off the trail. But for those of you that stayed the course, didn't get tired, discouraged, or frustrated, the topics we discussed should really provide a solid foundation for your future careers. So I hope you take what you have learned and use it to solve some important problems. And if I could somehow arrange it so you could all come back in 20 years and tell me how you've used this material, that would be a great event. But it's probably not going to happen. So lastly, I'd like to know what you think about the course structure, the course organization, the online lectures, and the websites. I would really appreciate any feedback you might have. In a certain sense, the course structure was kind of an experimental effort to enhance understanding. It's never clear when you're in the middle of one of these courses whether that in fact has occurred. So I will distribute a survey during our last regular class discussion, and I ask you to turn that survey in when you take the final exam. If you don't come to that last class discussion, the survey will also be posted as a PDF in week 16 of the website. I ask you to print out that survey, answer the questions, and again turn it in at the final exam. If you're outside the Purdue community and you're listening to this course, I would of course appreciate any email feedback that you can send to me, because we'll certainly revise a few of the lectures because of this course, and if there's topics or subjects that you think we should have included, I'd appreciate knowing about that. So, to put on a course like this requires a rather solid base, and there's a whole team of players at Purdue that have contributed immensely to this course structure. In particular, I'd like to thank Joe Sykos and Richard DeSuter, because they were involved with the taping of the lectures. There's been about 85 of these 25-minute lectures that have been produced. So thank you to those two for sticking with me during the long months it took to produce these lectures. I'd also like to say thanks to Michael McLennan and the HUBzero team at Purdue, who developed this HUBzero platform in which this whole course is based. So without their hard work, this type of course would not be possible. So that's about it, right? The semester is done. What's up next is to watch for the Physics 342 outtakes and bloopers video. That'll be available in week 16 of the course, and you're welcome to take a look at that. Some of the crazier things that have happened during our taping are going to be available on that bloopers video. So I'm going to close the book for the semester. I'm done. I've been talking all summer, and what I'm going to do while you watch the outtakes and bloopers is I'm going to go watch a baseball game. So